All right, here we go. Unit 7, Lesson 2, Part A. Trying to split these up into a couple videos to keep them short, nice and bite-sized. Today we're going to be starting a couple of days of work on what are known as differential equations. It's a deep topic. When you get to college, you're going to hear people talk about a whole course called diff-EQ, differential equations. But all a differential equation basically is, it's when we give you an equation that represents the derivative of a function. And so what we're mostly going to be doing is we're going to be talking about how to go from those derivatives back to the original functions. And it's a little bit trickier than you might think. It's not just straight up integration all of the time, because what we're going to find out later is you can have derivatives that depend on an input, x, but also on the output, y. It's kind of crazy. We're going to see all about it. So let's say we're given a function's derivative, and we want to get back to the original function, plus or minus some constant number. We can do that. We can do that by integrating. But here's the tricky part here. If we have the derivative of y with respect to x, right? So this is the change in y over the change in x at an instant. We actually can't just integrate that, right? It doesn't really have meaning to integrate just the variables of integration. So here's what you actually do. We separate these two things. And so I'm going to separate these equations by more or less multiplying by the infinitesimal change in x. Because what that's going to leave me with is the infinitesimal change in y, dy, is equal to 6x squared plus 6x plus 2 dx. And now, why did I do this little trick? I did this little trick because now, like I can do with any sort of operation I have in math, as long as I do the same thing to both sides of an equation, it's an allowable operation. On the left-hand side, I have the antiderivative, right? No bounds of integration of dy. What's that? It's 1 dy. So what this is asking is, what thing, if I took its derivative with respect to y, would give me 1? And that answer, of course, is just y, right? The derivative of y with respect to y is 1. On the other side, right, we're going to have a little bit more reverse power ruling to do. So we'd have y is equal to, this is all with respect to x, so that's good. We'd have, okay, x squared would go up to x to the third. But then in order to have 6, this coefficient would have to be a 2, right? Just thinking backwards through the reverse power rule, this 6x, well, it's going to have to be an x squared, but I need 6 when I use the power rule, so that's going to be 3. And then be careful, sometimes people forget those numbers there. This is just going to be 2x, right? And always check it in your head, check it backwards. Do these numbers, when I take the derivatives, give me back here? Okay, so here's what we have. But what did I forget? Mr. Burr, what did you forget? I forgot the plus c. Now here's the kind of weird thing. If we do the plus c on both sides, c stands for a constant we don't know yet. So it's kind of redundant to write it on both sides, right? On the left-hand side, you're saying, oh, this is some number I don't know. And on the right-hand side, you're also saying it, well, c plus c equals c, right? A number I don't know plus a number I don't know is a number I don't know. So what we typically do, we only write it on the one side. And we're going to write it on the side that's not quite solved for yet, as you're going to see why in a second. It's going to make our life easier. So we don't know what that c value is. And so right now, this is not much different than just taking a normal, right? This basically looks like I just asked you to take the antiderivative of 6x squared plus 6x plus 2. And really that is what you've done, but I'm dressing it up here in the language of differential equations. You're going to see why in a second. It gets trickier than this. Now we can plug in this initial condition. When x is 1, y is 2, and we can use that to solve for c. So if we plug those in, we'd have 2 is equal to 2 times 1 cubed plus 3 times 1 squared plus 2 times 1, right? You could solve all this out. Sorry, plus c, that's the whole point, is that we can solve this all out for c. So we'd have 2 is equal to 2 plus 3 plus 2 plus c. And we work this all out, right? I can probably, in the future, just leave this as an exercise to you. We'd have 7 plus c. So, of course, c there in that example, c in that example is -5, right? C is equal to -5. And so our final answer here, right, with c and everything, what I'd box on the final answer, y equals 2x cubed plus 3x squared plus 2x minus 5. And now, just to take a step back before we go on to a trickier version, what have we really done here? We have found a function that's derivative is 6x squared plus 6x plus 2. That's true. And also passes through this point, right? That is the important part here, is that this function also passes through the xy point, -1, 2. Okay? And so, right, why am I doing all of this extra, like separating the dy over dx, and when really all you did was take an antiderivative and plug in to find c? Here's why. And this is why, like I said, this builds out into all kinds of other coursework. Sometimes a function is not just dependent on another variable, but also itself. And so if you look at this, the derivative of y with respect to x is x squared plus 2x over 2y. All right, this is sort of the beginnings here of like multivariable calculus, is that you've got some function, right? It is some f of x, but it turns out that the derivative of the function depends on both the input x as well as y, the output. And so just a quick like, okay, where could I possibly see this in real life? Say you are heating up a piece of metal. Well, the rate of change of the metal depends not only on how long you've been heating it up, x, but also how hot it is, y, because the properties of metal change as their temperature goes up. And so both the amount of time that's passed and how hot it's gotten matter to the rate of change of the heat of the function. But anyway, here is what's nice about this. The same process applies. I'm going to take 2 steps here. I need to, and these are going to be called separable differential equations. I need to get all of my y's and dy's to one side, all of my x's and dx's to the other. So this one plays nicely, because if I multiply both sides by dx, I'd have dy equals x squared plus 2x over 2y dy. And notice I'm going through great pains here to avoid my least favorite term. What's my least favorite term? Cross multiplication. It's nonsense. You don't need it, because now I'm just going to multiply by 2y. And so what I would get here is 2y dy equals x squared plus 2x. For the record, if you like cross multiplication, right? Notice this is literally what I just did, cross multiplication. I'm just annoying, so I like to not do it because no one understands what they're actually doing. Yes, this in this case is just cross multiplication. But the important part is, right? Oops. And I forgot, let's see, what did I, oh, that should not have said dy there. That should have said dx, because that was what I multiplied by. What I can do here is, now that I have both of these all the way separated out, is just like in the previous problem, I can take the antiderivative. And so on the left-hand side, the antiderivative of 2y is, of course, y squared. The antiderivative of x squared plus 2x dx will be 1/3 x cubed plus x squared. And remember, I'm going to do this plus c out here only on the right-hand side, because we're only going to have really one unknown constant here. And so we take this to part 2, right, where x is 0, y is 2. We'd have 2 squared plus, or sorry, it's 2 squared equals 1/3 times, so they've made it easy for us, 0 cubed plus 0 squared plus c, 4 is equal to c. So our final differential equation, or close to it, would be y is equal to 1/3 x cubed plus x squared plus 4. But that's not how we write equations, right? We're not quite there. We need to take the square root of both sides. Now here's the tricky thing. Normally when we take the square root of y squared, well, the answer could be either, negative y or y, right? Normally we have that plus or minus out here. But what we need to think about is, what are we trying to find here? We're trying to find something where if I plug in 0 for x, I get out 2 for y. If I plug in 0 for x, I get out 2 for y. And when you plug in 0 for x, what do you get here? You get 4. And the square root of 4 is just positive 2, not also negative 2. So what we wind up with here is just y equals the square root of 1/3 x cubed plus x squared plus 4. And this would be our final answer, just the positive version of that. Okay? And so that is separable differential equations.